Most of the objects needed to be viewed or examined under a microscope are not visible to the naked eye. Apart from the details which can be enlarged under a microscope, the size of microscopic objects can also be measured. Dimensions, including length, width, or diameter, are often useful characteristics in classification and identification of organisms. The microscopes also help in following the growth and development of organisms and in observing abnormalities of biological specimens such as blood cells. In this lab, you will learn how to measure the size of specimens using two methods. By comparing the size of the specimens with the field of view diameter of the microscope, and by using ocular and stage micrometers. After completing this lab, you should be able to estimate the size of specimens by the field of view diameter of a microscope. Measure the size of microscopic objects using micrometers. We recommend you follow this PowerPoint presentation and fill all the answers in your lab report while watching. We will start with the first method, that is to estimate the size of a. To estimate the diameter, we use the following steps. First, get a piece of transparent ruler with a matrix scale in millimeter and centimeter. Then, at 4x objective lens, place the ruler on the stage so the millimeter scale could be seen in the field of view. Focus and move the ruler until the length of the scale along the diameter can be read. Normally, the diameter should be read at the value of approximately 4 millimeters at the low power objective lens. Determine the value with your eyes. For example, 3.5, 4, or 4.5 millimeters. Remember, this is only an estimation, not an exact value. This value can be used to calculate the field of view diameter at 10x and 40x objective lenses. In this slide, it can be seen that at 4x objective lens, the diameter of the field of view is approximately 4.5 millimeters. Remember, this is only an estimation. Next, to calculate the field of view diameter at 10x and 40x objective lenses, the following formula can be used. The field of view diameter of the lower power multiplied by lower magnification power divided by higher magnification power. At 4x, the field of view diameter is equal to 4.5 millimeters. At 10x, the field of view diameter is equal to 4.5 times 4 divided by 10. The answer is 1.8 millimeters. At 4x, the field of view diameter is 4.5 times 4 divided by 40. The answer is 0.45 millimeter. You see that the higher the magnification, the narrower the area that appears in the field of view. Once we know the diameter of the field of view, we can estimate the size of our specimens. we took the ruler away from the stage. In this lab, you will place a wet mount slide on the stage and use the 4x objective lens to find the specimen and bring the image into focus. In this online lab, we place a letter F and look at it using the 4x objective lens. Now, look at the picture on the right. This is your specimen at the 4x objective lens. What is the height of the letter F in comparison to the field of view diameter? For example, is the height of the letter about half of the field of view? Is it 1/4 or 3/5 of the field of view? Now, you can record the height of the letter F. It is about half of the field of view diameter as shown in the picture. Next, you can follow the calculation to estimate the height of the F. At 4x, the specimen height is half of field of view diameter. It's equal to half times 4.5 millimeters. It's equal to 2.25 millimeters. We know that the field of view is 4.5 millimeters. Then the height of the letter F is 2.25 millimeters. The next exercise is to estimate the size of a Spirogyra cell. Take a look at the picture on the left. This is an algal specimen observed under the microscope using the 40x objective lens. We have marked the boundary of one cell for you. For this picture, notice the length of the cell by comparing to the field of view diameter. Then, carefully draw a picture of this specimen in the lab report. Make sure you draw the picture to scale. Also, write down the size of the Spirogyra cell in comparison to the field of view diameter. We estimate that the length of each cell is about half of the field of view. From the slide number 5, we did estimate the field of view diameter of the 40x objective lens. The diameter is 0.45 millimeter. Now, we use the value of 0.45 millimeter multiplied by half. The actual length of a cell is 0.225 millimeter. We also use this value of the actual length of a cell for the next calculation. In your report, your drawing is much larger than the actual size of the cell. We can calculate the magnification of the drawing so that people who see your drawing have an idea of how many times your drawing is larger than the actual specimen. Let's take a look at this drawing as an example. The length of the cell in this drawing is 33 millimeters. You know that the actual length of a cell is 0.225 millimeter. The magnification of the drawing can be calculated as we show in this box. The length of the cell in your drawing divided by the actual length of a cell. So the drawing is 146.6 times bigger than the actual cell. The second method to measure the size of a specimen is by using micrometers. You will practice how to use division scales from an ocular micrometer for measuring the size of specimens. You need 2 pieces of micrometers for microscopic measurement. The first one is an ocular micrometer, and the second one is a stage micrometer. An ocular micrometer is a glass disc that fits in a microscope eyepiece. When looked through the ocular lens, marks with numbers 0 to 100 can be seen. The length of the marks on the scale depends on the degree of magnification. A stage micrometer is a slide with a known dimension edge on its surface. The stage micrometer is placed directly on the stage of the microscope. The scale of the stage micrometer was electronically divided and contains 100 divisions in 1 millimeter. We must calibrate the ocular micrometer using the stage micrometer. The ocular micrometer stays with the ocular lens, while the stage micrometer must be removed when you look at specimens. Remember that 1 division of the stage micrometer is equal to 0.01 millimeter or 10 micrometers. This picture is taken from the microscope with low power objective lens, 4x. The ocular micrometer aligns above the stage micrometer in this picture. At 4x, the ocular micrometer appears longer with the number 0 to 100 on it, and the stage micrometer is shorter without any numbers. We align the 0 mark of the ocular micrometer with the first mark of the stage micrometer. Once the 2 points have been aligned properly, then we scan through the scale mark to find a point where the marks of both scales align. Here, the 12th mark of the ocular micrometer aligns with 30 divisions of the stage micrometer. We already know that 1 division of the stage micrometer is equal to 0.01 millimeter or 10 micrometers. Then 30 divisions of the stage micrometer at 4x objective lens are equal to 0.3 millimeter. We can calculate the actual length of each division of the ocular micrometer at low power by dividing 0.3 with 12. The answer is 0.025 millimeter or 25 micrometers. Notice that the conversion from millimeter to micrometer is by multiplying the value by 1,000. If you cannot follow this step, don't worry. We will repeat again for the higher power objective lens. At medium power, 10x objective lens, The ocular micrometer aligns above the stage micrometer as shown in the picture. Notice that the size of the stage micrometer is bigger. Here, the 20th mark of ocular micrometer aligns with 20 divisions of the stage micrometer. We already know that one division of the stage micrometer is equal to 0.01 millimeter or 10 micrometers. Then 20 divisions of the stage micrometer at 10x objective lens are equal to 0.2 millimeter. We can calculate the actual length of each division of the ocular micrometer at medium power 10x by dividing 0.2 with 20. The answer is 0.01 millimeter or 10 micrometers. Once again, to convert millimeter to micrometer is to multiply the value by 1,000. We will calculate again for the high power 40x objective lens. At high power 40x objective lens, the ocular micrometer aligns above the stage micrometer in the picture. The stage micrometer is much more zoomed in. Here, the 40th mark of the ocular micrometer aligns with 10 divisions of the stage micrometer. We already know that one division of the stage micrometer is equal to 0.01 millimeter or 10 micrometers. Then 10 divisions of the stage micrometer at 40x objective lens are equal to 0.1 millimeter. We can calculate the actual length of each division of the ocular micrometer at high power 40x by dividing 0.1 with 40. The answer is 0.0025 millimeter or 2.5 micrometers. Now, let's do some exercises. If at the high power objective lens, the length of a Spirogyra cell was 35 divisions of the ocular micrometer, what is the actual length of this cell? From the previous slide, one division of the ocular micrometer at high power is 2.5 micrometers. We simply multiply 2.5 micrometers with the number of divisions of the ocular micrometer. Then, the actual length of this cell is 2.5 times 35 equal to 70 micrometers. The last exercise is to measure the size of a Spirogyra cell. We observe this wet mouse slide of a Spirogyra using a medium power 10x. We see that one cell of Spirogyra is equal to 22 divisions of the ocular micrometer. The actual size of one cell is equal to 10 times 22. The answer is 220 micrometers. In conclusion, today you have learned two methods for measuring the size of specimens. Please read the lab manual for further details.